Good morning, good afternoon. My name is Pawel Adamski. It's an honor to attend this conference and to give a presentation on control of inherently nonlinear vehicle in standardized driving cycles, whose co-authors are Paweł Olejnik and Jan Awrejcewicz. We are from Łódź University of Technology in Poland. In the beginning of my presentation, I'll introduce you to origin of driving cycle and will put a focus on two of them, NEDC and WLTC. Then I'll show you how I made it virtual and will show how a vehicle behavior changes with changing PID gain parameter. In the end, I'll discuss the result. I graduated in Łódź University of Technology and in French Arts Métiers Paris-Tech. Since 2015, I've been working on my PhD dissertation, which is analysis of ultracapacitor influence on electric vehicles, which lies very close to the research I'm presenting today. A driving cycle is a series of data points representing the speed of a vehicle versus time. When they are strictly precise, they are called either harmonized or standardized. I'll be using the latter term in the whole presentation. They are designed to assess the emission levels of car engines and fuel economy in passenger cars. Whereas in hybrid and battery electric vehicles, they are used to estimate the electric power consumption and driving range. First, such a standardized drive cycle appeared in Germany 1968. Later on, APA Federal Test Procedure in United States, and then New European Driving Cycle and its successor, Worldwide Harmonized Light Vehicle Test Procedure WLTP. I focused on the last two in this work. New European Driving Cycle is quite a simple test procedure with just a few characteristic points. What you can see is a chart presenting a reference speed in time during test. It is comprised of piecewise linear function with numerous discontinuities of its derivative. A full cycle is composed of 4 low-speed segments of 195 seconds and 1 high-speed segment of 400 seconds. Max speed is 120 km per hour. Here, a worldwide harmonized light-duty vehicles test cycle can be seen. At least one of it. WLTC is designed to suit to almost any light vehicle in the world, so there are different cycles for vehicles depending on their maximum speed and its power to mass ratio. Both diagrams presented are directly from a document of its founder. A reference is on the bottom of the slide. As you can see, a speed profile is much more probable and less artificial than New European Driving Cycle. The whole profile is composed of 1,800 points at each second of a test, and it is much more fluent. A typical standardized test is performed by a real car with environment simulated on a roller test bench, commonly known as a dyno, or on a flat road without wind. A standardized drive cycle is to be followed either by a driver or by an appliance substituting a human. Now I will switch to Research Tools and Results. First thing is that instead of a real vehicle, I used a virtual one in my research. Secondly, a virtual environment was simulated. Finally, a PID controller was used instead of a driver. A dynamical model of a four-wheel battery electric vehicle was established based on Newton's second law of motion. It takes into account transversal and rotational momentum, road forces, so all the resistance, and numerous car data such as mass or frontal area. I do not enter into further analysis of energy conversions in motor or its controller or in curvilinear movement of a vehicle. Just to give you an idea on the complexity of the LabVIEW model, I present here a model and a dashboard of a virtual vehicle. I have to admit that this model is composed of quite a lot of sub-models, so not everything is visible on the screen. Now the most crucial thing. What I do in this research is launching a simulation over NEDC and WLTC cycles with different PID controller gain and observing its influence to speed error, current, and energy consumption. Let's shift to the results. On the far left-hand side of the slide, you can see PID controller parameters. Proportional gain is equal to 1. You can see three graphs produced upon NEDC on the right. WLTC graphs are on the left. Upper graphs represent reference and actual temporal speed of the virtual vehicle. As any differences between blue and red line are hardly visible, the middle graphs show a velocity error in pink color and corresponding relative error in yellow. In the bottom graphs, you can see orange line representing orange current given in amps and state of charge, typically given from 0 to 1, multiplied by 1000. It's a green line. It is to be mentioned that the simulation on the left is aborted due to virtual traction, battery depleted. Although the battery should give about 70 km car range, the harsh current impulses depleted the battery in only 18.5 km, with an average energy consumption at 55.2 kilowatt-hours per 100 kilometers. It's interesting that the more artificial NEDC gives even greater energy consumption. It's 80 kilowatt-hours per 100 kilometers. For the same PID controller parameters. Also, max speed error is bigger in this case, 8 kilometers per hour comparing to 6 kilometers per hour. Another set of data is for decreased from 1 to 0.1 proportional gain of PID controller. It makes such a virtual car go further on one recharge, but to compare it properly for WLTC I maintained a shortened cycle. In this scenario, both drive cycles are much less energy consuming. In the other hand, on each side of the screen we can see an increase of maximum error. Now let's summarize the results. In these two tables, one can see a summary of the results. The upper one recapitulates just pure data, while the lower one gives you an idea on qualitative change in error and energy consumption due to PID controller decreased gain. Now let's move to discussion. Decreasing proportional gain of PID controller from 1 to 0.1 increased velocity error by 33 and 178%, but in the same time decreased energy consumptions of a vehicle by 63 and 78% for WLTC class 2 version 2 and NEDC driving cycles. The research shows that when replacing a driver by a controller, it is crucial to choose a well-adjusted controller and to supply it with optimal parameters to achieve goals. It is clear that a specific set of parameters that are best suited to go through one standardized driving cycle will not be the best option for another one. A possible way of improving desired behavior during a test would be providing to the controller a whole standard driving cycle to enable predicting the future. It would not make a vehicle more robust, but would guarantee better performance during a certain test. Thank you very much for your attention. Shall you have any question? Please ask now.